Welcome everybody to this series of lectures in the section of invited lectures in control and optimization. It's my pleasure to introduce the first speaker, Friedrich Eisenbrand from École Polytechnique de Lausanne in Switzerland. Before joining EPFL in 2008, Fritz had a professorship at the University of Paderborn in Germany. Fritz has received several awards, including the Leibniz Award of the German Research Foundation in 2004, the Otto Hahn Medal of the Max Planck Society in 2001, and he was a recipient of the from Alexander von Humboldt Professorship in 2011. The main research interests of Fritz lie in discrete optimization, in particular algorithms and complexity, integer programming, geometry of numbers, and applied optimization. Fritz is best known for his work on efficient algorithms for integer programming in fixed dimension, and also the theory of Latin planes. And today, Fritz will speak about recent results about the diameter of polyhedra. So first, I think we should welcome Fritz.
Thank you. Thank you very much, Monique, for the kind introduction. So I would like to talk about some recent results around a very visible problem, which is the diameter problem of polyhedra. And it's based on joint work with several people, with Nicolas Bonifat, Nikolai Händle, Martin Niemeyer, Alexander Rasborov, Thomas Woutros, and Santosh Vempal. Okay, so the motivation of this talk is linear programming, and more precisely the complexity of linear programming. Linear programming is the following problem. You're given a linear objective function C transpose times X, and you're given linear inequalities. The task is to find a point that maximizes this linear objective function, and if the polyhedron has vertices, if the columns of A are linearly independent, then there will be a vertex that is also an optimal solution of the linear program. So linear programming is a very important paradigm in mathematics, computer science, engineering, and many, many more disciplines. So we all know that linear programming is solvable in weakly polynomial time. This is known since the algorithm of Khachiyan, the ellipsoid method. Now, what does it mean, weakly polynomial time? That means that we are taking the binary encoding lengths of the numbers that encode the coefficients of our linear program into account. So the number of arithmetic operations that we're going to use or to apply in order to solve the linear program is not only going to be polynomial in the dimension and the number of constraints. Oh, no, I would like. It's not only polynomial in the dimension and the number of constraints, but also polynomial in the largest binary encoding lengths of a coefficient. Now, this behavior is natural for algorithms from the domain of number theory. For example, if you remember the Euclidean algorithm to compute the greatest common divisor of two integers, this is going to apply a number of arithmetic operations or divisions with remainder that is linear in the binary encoding lengths of your inputs, in this case, the two numbers A and B. And this is natural. In fact, one can prove that under certain model assumptions, this has to be the case, that a constant number of arithmetic operations for the greatest common divisor is not enough. This is a paper of Mansour et al. From 91. But this running time behavior seems unnatural for combinatorial problems like linear programming. Now, the open problem that is very visible and that I've mentioned in the beginning is the following: can linear programming be solved in strongly polynomial time? And strongly polynomial time would then mean that we apply a polynomial number of arithmetic operations where polynomial is depending on the dimension and the number of constraints only, and not on the binary encoding lengths of the input numbers. Of course, we also want to say that the numbers in the course of the algorithm should not grow too much. So the binary encoding lengths of the numbers should remain polynomial themselves. Now, what is known here is there are some sub-exponential algorithms in this model by Matuszek, Sharir, and Welz from the 96 and from Kalai in 1992. But this is the best complexity if we count arithmetic operations independent of the dimension and the constraints only. Now the simplex algorithm is the oldest algorithm one of the oldest algorithms to solve linear programs, and it works from vertex to vertex of a polyhedron. So here you see this is a vertex of a polyhedron. Now it goes along the edges of the polyhedron to go to an optimal solution. Here, let's say the task would be to find the point that is furthest up in the vertical direction. Now, the simplex algorithm was described by George Danzig in the 50s, and it's still a candidate for strongly polynomial time algorithms. Now, the diameter problem is connected to this question whether the simplex algorithm can be finally analyzed to run in strongly polynomial time, because as the simplex algorithm walks from vertex to vertex in the polyhedral graph, it must be the case that there is a short path between any two vertices in this polyhedral graph. Now, the diameter delta and m is the largest diameter of a polyhedral graph defined by m inequalities in dimension n, and the simplex algorithm, if it is polynomial, then the diameter has to be polynomial in n and m as well. So the conjecture that is out there and that has to be fulfilled in order for the simplex algorithm to run in polynomial time is that the polynomial Hirsch conjecture holds. So in other words, the following question is relevant if we want to answer the question whether the simplex algorithm runs in polynomial time. Is this diameter bounded by a polynomial in n and m? Now, as most of you know, the classical Hirsch conjecture for polytopes was even stricter. So this classical Hirsch conjecture said that the diameter is bounded by the number of inequalities minus dimension, and this was refuted by Santos in 2010. Now, what is known about the diameter of polyhedra? The best known bound is still basically up to a small improvement of, well, not quite that small, interesting improvement by Todd, very recent from 2014, is the bound of Kalayem-Kleitman, which says that the diameter is bounded by the number of inequalities to the power of 1 plus the logarithm of the dimension. And this improvement m minus n, so number of inequalities minus dimension to the power of log n, is a recent result of Todd. And there's a huge gap between the linear lower bound, so the counterexample of Santos yields a linear lower bound on the diameter of polyhedra, and the best known upper bound, which is by Kalayem-Kleitman. And in this talk, I want to mention some recent developments around this diameter question, and in particular some developments where I have been involved. And these are as follows. I will show you in a moment that the best known bounds are actually provable in light of a very simple abstraction that completely abstracts from geometry of linear programming, and is completely a combinatorial problem type. And we will see that the Kalayem-Kleitman bound holds for this very simple abstraction. In fact, you can show also the bound of Larman. Larman showed that a polytope or polyhedron in fixed dimension has a linear diameter. In this very simple abstraction that we'll see in a moment, also this bound can be proved. Together with Nikolai Hände, Sascha Rasbourov, and Thomas Rothfuss, we showed that in this abstraction, one can see that the diameter is not linear, so it is almost quadratic. But also here, there is a huge gap between what is known and from above and the lower bound that is quadratic. And interestingly, also many people thought about this in the Polymer 3 project. It seems that it's also difficult to close this gap in this very simple abstraction. And I think this is a tantalizing problem to try to solve this. I could mention some more details later. Now then I would like to mention a new upper bound on the diameter that is purely geometrical. So it depends on a parameter that is 1 over delta. I will mention this parameter, I will explain this parameter in detail later. And it will be polynomial in this parameter in the dimension. And the recent result that I have together with Santosh Vempada from 2014 shows that the random edge pivoting rule or variant of the random edge pivoting rule solves linear programs in polynomial time in the dimension and this parameter 1 over delta. Okay, and then I mentioned some open problems around these results. Now let's start with this very simple abstraction. The abstraction or the graph whose diameter I want to estimate is as follows. We have vertices and edges as usual. Now the vertices are subsets of an M element symbol set. And the subsets are all of cardinality n. And the only condition that I have on this graph is the following connectivity condition. Every pair UV in the vertex set is connected by a path in G whose vertices contain the intersection of U and V. Okay, so the vertices U and V, they are n sets, so sets of cardinality n, of this M symbol set. Now what are these symbols supposed to mean? The symbols are supposed to, well, they stand for the inequalities of the polytope. Now what this here is just simply saying is that if I have two vertices on a face of a polytope, then I can go from one vertex to the other without leaving this face. Okay? So here you see an example. I've now, for example, this, if this is the x1 direction, yeah, then this inequality which shows in the outside or shows outside of the screen would be inequality 1. And you see it is tied at all these vertices. Right? So I'm now naming the vertices by the inequalities that are tied at that vertex. By the way, I'm assuming, without loss of generality, that the polytope is non-degenerate. That means that exactly dimension many inequalities are tied at a vertex. Okay, and now you see that, for example, 1, 4, 5 is connected to 1, 2, 3 along a path that doesn't leave the intersection of 1, 4, 5 and 1, 2, 3, which is 1. Okay? So this is all. We're having a graph whose vertices are n element sets of n element subsets of an m element symbol set, and we have this connectivity condition. Okay. And what I would like to show you now is that this Kalayan-Kleitman bound, the diameter of such a graph is at most m to the power of 1 plus log n, can be shown along the lines of the proof of Kalayan-Kleitman themselves. Is there a question so far? Okay, so let's do that. Right? So we want to show that the diameter of such a base abstraction, we have two parameters, the number of symbols and the dimension, is at most the number of symbols to the power of 1 plus the logarithm of the dimension. Okay, how do we do this? We think about the following process first. Suppose we have two vertices that are farthest apart in our base abstraction. Let's call this first one S. And now we perform breadth first search, right? So we label all the other vertices according to their distance to S. Now this partitions my vertex set, if you like, into bags. And these bags, they are labeled with a distance. Now this inspires then the following idea. We partition the vertices into layers, layer 1 until layer L, such that now the condition, the connectivity condition that we had from before now reads as follows. Every set of symbols that is covered on layers I and J, so what does this mean? So suppose we have a set of symbols, and this set of symbols is a subset of a vertex in layer I, and is a subset of a vertex in layer J. Then this set of symbols is also a subset of a vertex in a layer that is in between. Okay? Now such a partition is called a connected layer family, and L is its height. And as I said, from the base abstraction we can get such a connected layer family by breadth first search, by partitioning the vertices into groups where each group corresponds to the vertices of a distance I to S. Okay, so let me show it to you this connectivity condition. So suppose we have here a vertex in layer I, so this is at distance I from S, this is at distance J from S, And this here is this subset of symbols that is both in this and in this vertex. Now our condition that we had before, our connectivity condition that we had before is saying there exists a path from I to j such that each intermediate path also contains this subset of symbols. Okay? But now how did we organize the layers? The layers, they are the vertices of a certain distance from S. Now when we go from here to here along the path, the distances cannot make a jump of 2, right? So they either stay the same, going from here to here, I don't change the distance to S, I go up by 1, or I go down by 1. So any layer that is in between, for example distance k, must appear on this path. Okay? Now we can prove the theorem of Kalayem-Kleitman in light of this base abstraction. And it's as follows. The height of such a connected layer family, so what you see here in this picture, those shall be the layers. And remember that these layers are sets of vertices, each vertex by itself is an n-element subset of m symbols. Okay? So now the height of such a connected layer family is at most m to the power of 1 plus log n. Okay? The proof is as follows. We first show the following recurrence. We show that the height of a connected layer family in dimension n with m symbols is at most twice the height of a connected layer family in dimension n with m half symbols plus the height of a connected layer family in dimension n minus 1 that has m minus 1 symbols. Okay, once we have this, we simply, okay, let's first show why this is true. Okay, so how do we prove this? What you have here is our connected layer family. Now we scan the layers top down just until the layer where we still have observed only half of the symbols. So that means the symbols that we count until here, until this one, until this layer, is going to be more than half of the symbols that are available. Similarly, from bottom up, we do the same, right? But now this means that in this upper part and in this lower part here, there must be a symbol that appears in the vertex down here and up there. Let's say the symbol is a blue symbol. Now what we do next is we look at the connected layer family that we get by taking all the vertices that contain this blue symbol, removing the rest, and then removing the blue symbol from all the vertices. This is going to be a connected layer family in dimension n-1 with m-1 symbols. This is this. And this height of the connected layer family stretches over this gap that we have to overcome. So we see that this recurrence here holds. Up here we see only half of the symbols. Down here we see only half of the symbols. So we have twice times the height in dimension n, and m divided by 2 rounded down, plus the height of this stretching connected layer family, this blue connected layer family, and we have this recurrence. Now once this recurrence is shown, we are going to expand this part again with the recurrence, and we see that the bound holds. So this is the proof of the Kalayem-Kleitman bound in this pure abstraction, in this very simple abstraction. Okay? Is there any question so far? Good. I also mentioned in the beginning that we can show another bound, which is also true for polytopes, which is that the diameter of a polytope in fixed dimension is linear. This also holds for our base abstraction with a slightly worse constant than in the Larman and Barnett bound, which is geometrically proven. Okay? So what do we have here? We have here a very simple combinatorial abstraction that doesn't use any kind of geometry. And the best known bounds for the diameter problem of polytopes carry over, basically, to this abstraction. Now, it turns out that the lower bound that we can prove here is better than linear, but not much better. It's quadratic, so it's quadratic in the dimension. We can show that if we have a connected layer family or base abstraction dimension n with O of n symbols, then the diameter can grow as much as n squared divided by log n. Okay. What I also would like to mention is a recent result here of Francisco Santos, who proved that pure simplicial complexes can have exponential diameter. Now, what is such a pure simplicial complex? So this is like our base abstraction, except that we remove the connectivity condition that we had, and we replace it by setting edges explicitly. We are saying that a vertex is connected to another vertex if their intersection has cardinality dimension -1. So this is what happens also in polytopes or in polyhedra, right? If we have a vertex of a polytope here and another vertex here, and the inequalities that are tied at both are exactly of cardinality n-1, dimension -1, then they're connected by an edge. So this alone does not suffice to show a sub-exponential upper bound on the diameter. What Francisco Santos showed is that this can be exponential. Okay. Yeah, so what I would like to mention here, and this is the message that I try to carry over, is that in this simple abstraction, the truth seems also not easy to find. There is a conjecture of Nikolai Händler which says that the height of a connected layer family or the dimension of such a base abstraction is at most, excuse me, I confused here the dimension and the number of constraints. So take m, n being the number of constraints, d being the dimension, is at most a dimension times number of constraints minus 1 plus 1. So this would be quadratic. And you can now take a subsolver, code this theorem as a satisfiability formula, and let the computer see whether it's true, at least for some parameters n and d. Now what you see here is it's true. This can be proven that, for example, if d is equal to 1 and 2, then this conjecture holds. And if n is 1, 2, and 3, then this conjecture holds as well. What you see here, these pluses, this is the region where we could find out the truth with the subsolver. So this conjecture is supported by small examples. But it seems to be that proving this conjecture is not easy as well. But if you would prove it, then you would have an upper bound in the diameter of polytopes as well. Okay? Good. So now I would like to come to my second part of the talk, which is a new upper bound and this on the diameter of polytopes, and this new upper bound uses geometrical aspects. Now, what is this parameter 1 over delta that I mentioned in the beginning? Suppose that we want to solve a linear program, maximize C transpose times X, AX less than equal to B, where we assume without loss of generality that each row vector of A is scaled so that it has norm 1. So all the rows lie on the unit sphere. Now, what we say here about what this delta is a lower bound of the distance of a row AI. So pick any row AI, and now pick a subspace of Rn, a subspace of dimension at most n-1 of Rn, that is generated by other rows of A. Now look at the distance that AI has to this subspace. So this distance should be at least delta, right? So this is our parameter delta, or 1 over delta, that I mentioned in the beginning. And now what I would like to show to you is that the diameter of a polytope is polynomial in 1 divided by delta and the dimension, and independent, in fact, on the number of constraints. And later, if we have time, I will also show you how to solve a linear program in polynomial time in 1 over delta and the dimension only, independent on the number of constraints. Okay, so what we have, this property has a name. It's called delta distance property, and it was introduced by Wunsch and Röglin in 2013. I mentioned their result in a second. Okay, so we are assuming now that our matrix A of our linear program satisfies the delta distance property. Okay, for now this delta distance property seems like an arbitrary property. I try now to convince you that it has a good motivation, and the motivation comes from total unimodularity. This is the first motivation that I will give to you. And total unimodularity is an important concept in combinatorial optimization. What you see here are some papers where the authors have shown polynomial upper bounds on the diameter of polytopes. For example, if P is a flow polytope, then we have a quadratic upper bound. This was shown by Orlin. If we have a transportation polytope, then we have a linear upper bound. And this here is a very interesting result that I will mention later in greater detail. We extend this quite a bit. By Dyer and Fries, they have shown that if A is totally unimodular, right? So if this matrix A is totally unimodular, that means that each A is first of all a 0 plus minus 1 matrix, and each K by K minor is bounded by, in absolute value, by 1, right? Then we have an upper bound that is polynomial on the diameter as well. Okay, so here I've mentioned already that the constraint matrices that describe flow polytopes and transportation polytopes, they are totally unimodular. So totally unimodular matrices have the delta distance property with delta is equal to 1 over n. Okay? So you remember that we have a bound on the diameter which is polynomial in 1 over n, in 1 over delta and n. Now, what we have then is we can show polynomiality of total unimodular or polytopes that are described by total unimodular matrices. But we have more than that. So this is an example of a matrix which is not totally unimodular, but which satisfies the delta distance property with a large delta as well. What we consider here is the so-called edge node incidence matrix of a graph. So if I'm given a graph, the matrix has an entry for every edge, and so a row for every edge, and a column for every vertex. Now, in this row here, for example, I'm encoding an edge. I'm encoding for, it could be this edge here, right? If this is vertex 1 and this is if this is vertex 2 and this is vertex 3, then this edge here will be encoded by this row. So what you have is a matrix which has 2 1s in every row, and this row is representing the edge of a graph. So that's the node edge incidence matrix of a graph. It's very important in the stable set problem, for example, and also in vertex cover. Now, the largest minor of such a node edge incidence matrix can be exponential. In fact, it turns out that the number of odd cycles, 2 to the power of number of odd cycles in your graph, is the largest minor that you can have. So it's far from being totally unimodular. But the delta, so this distance that we had from before, you pick one row, and you pick n minus 1 other rows, and the distance of this row to the space generated by the other rows is at least 1 divided by the square root of number of vertices. Okay? And also, unlike in totally unimodular matrices, which are plus minus 1, 0, the rows do not need to be integral or rational. So this is a purely geometric property, this delta distance property. Okay. Good. So now I would like to show to you how to prove this upper bound on the diameter. And the proof is quite natural. We will go through all the details. It's not going to be long. But here's the idea. We are assuming that, again, that our polyhedron, P, is non-degenerate. What does this mean? Each vertex has exactly dimension many tight inequalities. This is without loss of generality. We could just simply perturb the right-hand sides B a bit, and then the diameter would only grow. Now what we do next is we associate a volume to each vertex. And we want to bound the diameter, right? So what we actually have in mind is we have two vertices and we run breadth first search, right? So these vertices, they start to discover more and more vertices, and at some point they discover a common vertex, right? And at this point we have to multiply by 2, and this would be an upper bound on the diameter. Now, how can we upper bound this moment in time where they meet, where they see a common vertex? This we can do by associating a volume to each vertex, and now by running breadth first search until the total volume of vertices that we've seen exceeds half the total volume of vertices itself. Right? Then by the pigeonhole principle, there must be one that they have both seen together, because the total volume, or the total volume of vertices that has been observed by the two nodes cannot exceed the total volume of vertices itself. Okay, so this is the idea. Now, what is supposed to be the volume? Now, this is a polytope, and this is a vertex of a polytope, and what you see here is the so-called normal cone of this vertex. The normal cone of this vertex is a set of all objective function vectors that would give you this vertex as an optimal solution. Now what you see here on the right is another vertex, and you see its normal cone. Now two vertices, they are neighbors of each other if and only if their normal cones share a facet. Okay? So we see that normal cones do not intersect in interior, so this is a good candidate for volume. And two vertices are neighbors if and only if their normal cones share a facet. Okay, so here I've just taken the apex of the normal cone and I moved them into 0 as it should be, right? So those are the normal cones of this vertex and this vertex respectively, and you see they share a facet. Okay, good. So the volume of a vertex now is going to be it's the volume of its normal cone if I intersect it with the unit ball. This is going to be the volume of a vertex. And now I need to show that the volume rapidly expands when I do breadth first search. In other words, I have to show that the volume exponentially increases. Okay, and this is done with the following lemma. If you have a subset of vertices whose volume is still bounded by half the total volume will be the volume of the unit ball itself, right? Then the volume of the neighborhood of I is at least this expression here. So this is something which is polynomial in delta and 1 over n times the volume of I, so the volume of the set of vertices with which we start. So once we've shown this, we are done, right? Because we start with a vertex, and this vertex has a volume. Now, it's pretty clear that the delta distance property shows that this volume is at least delta to the power of n divided by the volume of the standard simplex. Right? That's pretty easy. Now, the total volume is bounded by 2 to the n, and this should be greater or equal to the volume of vertices we see in iteration k. And now, this is, if we use this formula here, at least 1 plus this expression to the power of k times delta to n divided by n factorial. And from here, the theorem follows easily. We have rapid expansion of volume, exponential growth of volume. The diameter is then bounded by the dimension to the power of 2.5 divided by delta times the logarithm of n divided by the dimension. Okay, now, how do we show, is there a question at this, until here? Okay, so now, how do we show this? How do we show this rapid volume expansion? And this is an idea that is also present in geometric random walks, here specialized to the diameter case. Okay, so this is a set of vertices, and now this set of vertices has normal cones. We intersect these normal cones with a unit ball, and we take the union of these normal cones. Now this set could look something like this. Now we've seen that a neighbor of a vertex shares a facet. Okay? So these facets, they have to dock on this surface here. right? So this is a surface which needs to be covered by the neighbors in the next iteration of breadth first search. So we need to cover them. Okay. So now this expansion lemma follows from two inequalities. What is this one here? This says the dockable surface of a single cone. A single cone offers some surface to cover this, right? So this dockable surface of a single cone divided by its volume is at most n squared divided by delta. And now if you take this cone here, then we want to lower bound the dockable surface that it offers that needs to be covered, right? And dockable surface divided by the volume is greater equal to square root of 2n divided by pi. So once we have these two inequalities, we see here, and this is the philosophy here, right? So all this surface needs to be covered. The vertices in the neighborhood of I have a surface to offer, and this must be greater than the total dockable surface that needs to be covered. And then we have this inequality from before, and this one, this inequality, this is the inequality here, and this gives us our rapid volume expansion. Okay, so the volume of the neighborhood is at least this factor times the volume of the set I itself. Okay, so it turns out that this inequality here, so the dockable surface of a vertex itself divided by its volume is at most n squared divided by delta. That quickly follows from the delta distance property, right? Because you take a facet of your cone, and now you know that the cone's height is at least delta, right? So delta divided by n times the area of the facet is a lower bound on the volume. Okay? So we get here then, by multiplying by n, the total number of facets that we have, that the dockable surface of one cone divided by its volume is at most dimension squared divided by delta. Now, what about this one here? This one was relating the dockable surface that needs to be covered by this bunch of cones, and relating this dockable surface divided by volume ratio with this number here, 2n divided by pi square root of. And that's pretty easy. It's just simply the following observation. If you have, let me just, I know I shouldn't do that, but if you have a bunch of cones, and now you want to keep the volume the same, but at the same time making the dockable surface as small as possible, then you just take a spherical cap and the convex hull of a spherical cap, right? That's an isoperimetric inequality. So this is just an isoperimetric inequality, and the observation that this ratio here is worst case for the half-ball. Remember that the volume of vertices that we have seen so far should not exceed the half-ball, right? So then this ratio here is at least the one of the half-ball. Okay. How am I doing in time?
10 minutes.
10 minutes, okay, good. So if there's no question, then I would like to show you now how one can make this result algorithmic. Yeah? So now we have, what have we done? Maybe we should wrap up again and say, what have we done? We've proved that if we are given a matrix with delta distance property, and now we can choose any right-hand side for ax less than or equal to b, any right-hand side, even irrational, it doesn't matter, then the diameter of this polyhedron is bounded by this expression. It's polynomial in 1 over delta n. It turns out that we don't need the delta distance property, which is a global property of the matrix. We just need it locally at every vertex. Yeah? So this is even less restrictive. You can easily show that you can have polytopes with exponential number of inequalities. Yeah? But as long as we have the delta distance property locally at every cone, we have small diameter. And I think this is not, well, this gives you at least another indication where you shouldn't search for an exponential upper bound, lower bound. Okay. Good. So now I would like to mention in the last 10 minutes how to make this result on the diameter, which is non-constructive, how to make it how to turn it into a polynomial algorithm. Now there's some history to that, and it's this aforementioned paper of Dyer and Fries, already from 1994. It's a very nice paper, where they provide a polynomial randomized simplex algorithm for totally unimodular LPs. Right? So also here the right-hand side can be even irrational. As long as the matrix is totally unimodular, that means 0 plus minus 1 entries, and each k by k minor is bounded by 1, we have a polynomial algorithm for the linear program, strongly polynomial algorithm. Now Brunsch and Röglin showed that the shadow vertex method finds a short path between designated vertices. So if I give you vertices of a polytope, then you can apply some variant of the shadow vertex algorithm, and you could get a path that joins these two vertices, that is polynomial in the dimension, number of inequalities, and 1 over delta, where delta is our delta from the delta distance property. Now what I would like to show to you is just a sketch, just some basic ideas, how to turn our diameter bound into an algorithm. And this is a result that I recently had with Santosh Vempala. The random edge variant of the simplex algorithm solves linear programs in expected polytime in the dimension, number of inequalities, and 1 over delta. And what is interesting about this is that I think interesting about this is that the number of pivots is polynomial in the dimension and is 1 over delta only. So we don't need to have, the LP could have exponentially many inequalities. If you have some implicit way to find the neighbors of a vertex, then we can use this algorithm and we don't have to write down the LP. And this is an analogy to the separation optimization principle of the ellipsoid method. I come to that later. Okay, good. So what you see here is the space of cones. So I didn't draw a picture anymore of the polytope, but only of the cones. You remember these cones, the normal cones of our vertices. Now if we start within the cone of the feasible solution, for example here, and we leave this cone only through a facet, for example at this point here, then we can wander around in this ball and we can keep track of the cone we're in, right? Because going through a facet is just a pivot, so we know the new basis or the new cone to which this point belongs to. So as long as we walk through facets, we are in good shape. We should not cross cones in one step as well, so that means we shouldn't go from here to some other cone here as well when we walk around this ball. Then we can keep track of the optimal basis. Okay? So you see here, this is a walk where we started at our basic feasible solution cone, and then wandered around a bit, and then went finally to the cone of where the objective function vector C resides in, and that this is the optimal cone, and we have solved the linear program. Okay, so now how do we do this? We do this with a random walk, and this is just a sketch. There are some details that I gracefully skip. So we partition the space of cones into small parallel pipettes, and this is as in Dyer and Fries. So you see here that I take the parallel pipettes that are generated by the vectors of the normal cones, or generators of the normal cones, and I tile each normal cone with such a parallel pipette, and you see that nicely connected via facets. Even when we go now from one cone into the next, they're connected by a facet. So the reason why we are tiling is that, one, we can never skip a cone, and we only go through facets. This is reason one. Reason two is that now when we place a Gaussian somewhere around C divided by 8, yeah, and now we take the Gaussian measure of these cones, then neighboring cones will not have a Gaussian measure that is too much away from each other, at least as long as it's in the unit ball. So the unit ball here actually does not matter for the algorithm that I'm going to show to you, it's just for analysis purposes. Okay? So we consider this Gaussian here to see it has its maximum at C over 8 and then drops off quickly. Now what we do is at a given parallel pipette, now we are in this cone, we choose a neighbor uniformly at random, and then, once we have make this transition, this probability 1, this is the measure of the neighbor divided by the measure of the cone we started with. Now if you do this, people working in Markov chains, they see that this is a lazy time reversible Markov chain with stationary distribution which is proportional to the measure of these parallel pipettes. Okay? Now, if this T0 here is small enough, then this random walk will attract very strongly in this region here, and we will end up close to C. Okay? Now, for Markov chains, you have to show good conductance, and this follows again from an isoperimetric inequality, and I spare you the details. But again, here the fact that we have small parallel pipettes instead of these cones. You know, we could say, don't take the parallel pipettes, take the cones themselves, and look at the measure of these cones and so on. This is all a bit complicated to compute the measure of the Gaussian measure of these cones. For the parallel pipettes, it's easy, at least approximately. Okay, then here you see an image of such a random walk, and once we're close to C, we can retrieve an inequality from the optimal basis, and this is our result. The result is this. There's a random edge pivot rule that solves a linear program using poly n 1 over delta pivots in expectation. So some remarks on how we prove this. We bound the so-called S conductance of the random walk from below, and this is polynomial in delta and inverse polynomial in dimension. Then we use a result of Lovász and Siminowicz, and after a polynomial number of steps, the current parallel pipette is close to the optimal one with high probability, and we extend the result of Cook to retrieve an element of the optimal basis. Okay, good. So now let me come back to this analogy to separation and optimization. One of the most important consequences of the ellipsoid method is that a linear program does not have to be explicitly described. So an algorithm for the separation problem implies an algorithm for optimization and vice versa. This is described in the paper of Krötschel, Lovász, and Scriber from 1981, and it has tremendously many consequences in combinatorial optimization. Now our result has polynomial running time as long as the neighbors of a vertex can be computed, right? That's the nature of the simplex algorithm. We don't need the linear program explicitly as well. And if we have the neighbors of a vertex, then we can compute the transition probabilities. So the LP does not have to be given explicitly as well and can be exponential, meaning exponential number of inequalities. All right. So finally, I would like to mention now the open problems that I think are tantalizing around this subject. The first one is a super polynomial lower bound for the diameter of the base abstraction. Right? This seems to be doable. I mean, we forget about all geometry aspects, and still this is a tantalizing problem. Right? If not, show this conjecture of Feynman. Now this algorithm that I showed you in the end is randomized. It would be interesting to find out whether we can get also a deterministic simplex algorithm that solves linear programs in poly time n 1 over delta. And now I told you that the diameter result holds also for local delta distance property. So delta distance probability at cones themselves. And the question will be, can one achieve a corresponding algorithmic result? So our algorithmic result needs a global delta distance property. Global delta distance property meaning, as I have described to you in the beginning. And finally, now, is it possible to exploit the fact that we only need n 1 over delta, poly n 1 over delta many pivots to find the optimum solution in a similar way as it was done for the ellipsoid method, now here with the simplex algorithm for combinatorial optimization problems, submodular functions, etc. So if this would work, this would be very nice, because then we would have a generic machine for combinatorial and strongly polynomial time algorithms. That was it. Thank you very much.
Thank you very much. So it's time for a quick one
not follow which assumption you were carrying on. I think it's criticizing this about degenerate and non-degenerate. Because the theorem was for non-degenerate molecules.
Right.
And then you said you can make it non-degenerate. Then
right.
It's degenerate, of course, the usual trick is to disturb the right-hand side. But now you also allow to have an exponential number of inequalities. And then it may be, I don't know whether it's true or not, that the diameter may blow up because the number of vertices you create may be very large.
You're right. So, but
you have an argument for that.
Yes. So if I do this perturbation, every vertex becomes a cloud of vertices.
Yes.
But the neighborhood between clouds of vertices is the same as the neighborhood of the original vertices. So the diameter now just becomes larger. Right? I have to go in the cloud and go around in this cloud and then exit. So that in any case, the diameter just grows, even with an exponential number of inequalities. And I can find, no matter how many inequalities I have, I can find a small epsilon with which I can perturb the right-hand side.
You want to have this polynomial bound on that, and could it not be that this is now low? So you don't get a polynomial bound on the disturbed thing, but this polynomial bound may not be polynomial for the original.
No, it is because the number of inequalities is irrelevant. So the bound that we have is in the dimension and this 1 over delta. So it's irrelevant of the number of inequalities. It can be as many as you like.
Would your algorithm be efficient in terms of some statistics that say most rows do not have a small delta?
That's a great question. I think this is exactly, that's a great question. Can you repeat the question?
Can your algorithm be made efficient? Would it be efficient if you have some statistic that says delta is not too small for most rows rather than small as...
So I think this, as I said, this is a great question, and I think the answer is yes. But you need more than just you need more than just quantifying the, let's say, the percentage of cones that is bad. You somehow also need how they are localized, right? They shouldn't cluster. They shouldn't cluster. They should be somehow spread. I suspect that something can be done. So I believe that truly this simplex algorithm, Goodhart's old simplex algorithm, and pivoting, random pivoting, has potential.
Okay, so thank you very much again.
Thank you.
So we start the next lecture. But excuse me, please, I have a from the organizing.
Thank you.